Here's an example where instead of term-by-term differentiation, we would use term-by-term integration, which works basically the same way. We're going to have to start with the Maclaurin series for 1 over 1 minus x, which is the simplest of all the power series. It's just x to the k. 1 plus x squared plus x cubed, x to the fourth, however long you want to write out those terms. And to get natural log of x, I'm going to have to start by massaging this a little bit to get 1 over x. And something to note is that because this comes from the geometric series formula, it works for absolute value of x is less than 1. This will also get manipulated a little bit to turn into 0 minus x, 0 is less than x is less than 2. And how it gets manipulated is we get 1 over 1 minus x. Notice that the 1 minus 1 cancels, the negatives cancel to get us 1 over x like we're supposed to have. Notice that when you do this, your absolute value of x becomes absolute value of 1 minus x, and you can see really quickly you get the appropriate domain of convergence. Okay, that's not the hard part of the problem. Instead, what we're going to do over here is replace the x's with 1 minus x's. So we get 1 minus x to the k. So that gets us a 1 plus 1 minus x plus 1 minus x squared, 1 minus x cubed, so on and so forth. And so what we'll do now that we have this new series here is we'll go ahead and integrate 1 over x dx because that's the natural log. And because we can do this term by term, oh, I'm getting ahead of myself. This isn't really a power series, is it? At least not the way we're used to seeing it, because the x isn't has this negative in front of it. So before we do anything, let's go ahead and rewrite this just a little bit. We could rewrite this as, instead of 1 minus x, we could write that as negative 1 to the k, factoring out that negative 1, x minus 1 to the k. K equals 0 to infinity. And now if we write it out, the terms, we'll still start with a 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, so on and so forth. And that might make integration and differentiation a little bit easier now that we have no coefficient on that x. Now, natural log of x. The integral of 1 over x dx. I'll integrate term by term, and the negative 1 to the k has no x's in it, so I don't have to worry about that. I'm just integrating x minus 1 to the k with respect to x. So I add 1 to the power and divide by the new power. And what happens then if I expand this out? This is it. That's all I've got to do, right? I expand this out, and I get x minus 1 to the 1 divided by 1 minus x minus 1 squared divided by 2 plus x minus 3, 1 to the 3 divided by 3, so on and so forth. Except, what did I do wrong? Well, it's integration. It's integration, so there's always that plus c. Always that plus c we got to worry about. So let's back up a little bit. So there's a plus c, plus c. How the heck do I handle that? Well, let's go ahead and plug in something we know about for natural log. We happen to know that the natural log of 1, k equals 0 to infinity, negative 1 to the k, x minus 1 not x anymore, 1 minus 1 to the k plus 1 all over k plus 1. That's going to be plus c. Natural log of 1 is equal to 0. So what happens? Well, it's very tempting to just cross all of this out and say, hey, c is equal to 0. And you're close, but keep in mind that we have, and you would be correct. I was worried for a moment that you would not be right because x to the 0, 0 to the 0 is equal to 1. However, because of this exponent, all the exponents are at least 1, which means that 0 to any exponent bigger than 1 is zip. This all zeroes out, all goes away, and we do get that c is equal to 0. So it's just something you have to be aware of with integration. It's not too big of a deal because you're usually adding 1 to that exponent to prevent 0 exponents. Okay, c is equal to 0. That's great. Now we can scratch out that c. Now we can call this our integral. And if we want to expand that out, we could get what I was trying to write earlier, x minus 1 to the 1 divided by 1 minus, for the next term, x minus 1 to the 2 over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4, so on and so forth. That would be the first few terms of the infinite length polynomial. And let's just go ahead and take a look at a graphing calculator, see what that would look like. Here's my natural log. I only care about between 0 and 2, so this is what it looks like. And then, sure enough, it starts to kind of go away as we get to 2 right here. But between 0 and 2, it looks like mostly it's fitting pretty well. If I wanted it to fit better, well, I'll just add more terms. And eventually it should squeeze in as far as I need it to get that convergence between going up to 2. We can't we can't hope for anything better than that because that's my domain of convergence there.